Okay, so today's topic will be about sampling. I asked you yesterday to revise this concept. It was covered in the signal and system course, but we will be needing it here. So it's a good idea to revise this concept. So basically, let's remember our mixed signal system. So we will have an voltage signal coming that we will need an anti-aliasing filter. Now we will discuss the details of this. Why do we need the anti-aliasing filter? And then we will have a sample and hold circuit. Then we will have the ADC followed by the DSP, digital signal processing, and then the DAC, and then a reconstruction filter. Also, we will come to this. So this is the generic structure of a mixed signal system. So you remember that in order to convert my signal into a digital, so first I need to sample the signal. And then the second task is to do quantization. And then after doing those two and linking it to a reference voltage, we will be having a digital output. And basically this is all done in the first part of the circuit. So first we will have the sample and hold circuit. It will perform the sampling function. So we will have here just samples. And the ADC will do the quantization and convert them into digital bits, as you can see here. So now they just don't have a voltage value, but they have a digital codes for those voltage values. And then you will perform whatever functionality you want on it in the DSP part. And then the DAC, it will basically convert back the output after doing the digital signal processing. We need to convert it back to analog. So the DAC will do this functionality. We will describe it also today. And after that, you will need a reconstruction filter. That we will come to definition of anti-aliasing filter in a small time. Just this is the generic at this moment. I just want you to know the flow and in the details of each part, what it will be doing. This is what we are going to discuss entirely in the course. Okay, so just to refresh our memory about the sampling. So the sampling is basically when you have your original analog signal or a voltage continuous in time, continuous in amplitude signals. We want to take the sampling process is basically you just take, let's say, a snapshot of those signals. So how to decide, is it a good sampling process or it's a bad one? What is the criteria that tells us how good my sampling or my sampler is? Basically, if I am able to reconstruct my original signal after taking those samples, doing some processing in it, will I be able to restore the original signal? If that's a yes, this means my sampling is good enough. If I'm going to lose this information after the sampling process, then my sampling is basically inadequate and it's not good enough for me to reconstruct the original signal. So if we look at this original signal that we need to be sampled. So in B figure, you can see that I am sampling so frequent, means I'm taking samples or snapshots from the signal after every short amount of time. So after short duration, I am taking a sample of the signal. This means I have a high sampling rate, means the time difference between two samples is very short. You can see it here, it's this tiny distance between any two samples. They are basically, this is tells me how frequent or that I am taking my samples. Now, in case of a medium sampling rate, you can see the distance between two samples in time has increased. So I'm taking less frequent samples as compared to a high sampling rate. While in the case of a low sampling rate, this distance has become much more bigger than it was in case of the medium and high sampling rate. So we will see what is the criteria again to tell me which one of them should I use, I mean, and each one has advantage and disadvantage. We'll talk about it. So basically the criteria that tells me if I am doing a good sampling or not is that will I again be able to reconstruct my original signal from these samples or not? Now, someone may say that even on this low sampling, will I be able to reconstruct this original signal? Maybe not. Maybe another signal can have the similar types of crosses those change very fast and crossing at the same those points. So there can be multiple more options of the sample of a signal that basically crosses the same point. So this can be a bad sampling rate for the signal. So what is the exact criteria that I decide that my sampling frequency? And the definition of my sampling frequency is basically the number of samples that I take per minute, and it decides, so the sampling rate is 1 over TS, and TS is basically time difference between two samples. So when my FS goes up, means I increase my sampling frequency, the time between the two samples basically goes down. So TS goes down, and this is an inverse relationship. So the sampling theorem tells us that basically your sampling frequency should be at least equal to 2 times of your bandwidth of your signal. So if my bandwidth, let's say 1 kilohertz, minimum sampling frequency that I should be using in order to reconstruct my signal correctly, it should be 2 kilohertz. So double of my signal bandwidth. And this sampling frequency, we call it the Nyquist frequency, and or the Nyquist rate. So again, if we, in this example, if we have an analog, a signal that is changing between 0 and 3 kilohertz, we should, what is the proper sampling frequency that we should be selecting? The minimum sampling frequency is 3 kilohertz times 2, and this is equal to 6 kilohertz. So this is the minimum frequency that we can be selecting in order to reconstruct my signal correctly. Now, if we want to look at it from a point of view, in a pictorial point of view, so you can see this is my original signal, and this is how it looks after sampling. It's a discrete in time, so it happens at equal distance, and each one of those samples, I can give it the index of the sample. So x of n is not a function of t anymore. It's a function of n, which is n is an integer multiplied by t, and the t is the same as ts, the distance between those sample times. Okay, so in reality, how the sampling process, or in math, how it happens, it's basically you are multiplying your signal in the time domain with a train of pulses, and then you are capturing your signals on those by multiplying them with a train of pulses in order to get your sampled signal. So if we want to look at at it in the frequency domain, as you remember that what we have a multiplication in the time domain, it converts into convolution in the frequency domain. So now after we convolute the frequency response of our original signal with the frequency response of the train of pulses, we end up with this relation. So our sample signal, this is the sample signal in frequency domain. Is basically the convolution of your original signal shifted with the train of the pulses, and we end up with 1 over TS. Now we will have a periodic set of copies or images of the frequency response of our original signal at different copies or multiples of f of s. It would be better to look at it in a figure. It would be easier to understand. So if this is my original signal in the time domain, so this is a time domain signal, and here the frequency domain of my original signal. So this is the original signal that I want to sample. It's a band limited signal. It has a bandwidth of B here, a maximum bandwidth of B. And this is my sampling train of pulses. So it also looks like this in the frequency domain. Now, after I multiply them together in the time domain, there will be a convolution in the frequency domain. So this is what it will look in the time domain, a train of pulses having different amplitude, but in the frequency domain, we will have the same frequency response of our original signal. It will be have multiple images at every copy of every multiple of our sampling frequency. So at fs, at 2fs, at 3fs, until infinity, and again at minus fs, minus 2fs, and minus 3fs. So this is what happens in the frequency domain if we see the sampling process. So now what again, the same thing, we will have scaled and replicated copies. We call all these copies as aliases. Now imagine that we have basically in our original signal, let me erase those parts here. I just want to select different color. Imagine that I have another signal that is here above the bandwidth of my signal. So now and this signal is not part of my desired signal. It's just any noise or interference or anything. Now, when I'm going to do sampling, what's going to happen? This signal will again appear here. It will appear here as well. So it will appear, and it might even come more near to my signal. So now it will also fold back here around 0. So now you can see it has came into my range of interest. And this is basically something bad. It is going to affect the quality of my signal. And that's why we need an anti-aliasing filter. So what is this filter supposed to do? It's supposed to cut any signal. Before I do the sampling, it's supposed to cut any signal that is outside my bandwidth of interest, so that this interference after the sampling process, it doesn't come and hurt my original signal. Somebody's raised hand. Anyone have question? No question.
Ma'am, can you repeat about the anti-aliasing filter?
Yes. So basically, again, if there is any signal that is beyond your band of interest, once you will do sampling, it will also be the same. The sampler does not understand that this is an interference that I should reject. It will consider it as just a signal that is coming to it. So it will do the same exact process of sampling. So it will sample this noise, and it will come within our band of interest. So it will be, after you multiply it, basically, let me go to the previous. If you look at it in the math perspective, it will again be come within our band of interest. So this omega will be, when k is equal to 0, it will come into our band of interest here. This or the bad noise that was originally here. So now it has came on top of my original signal. So I cannot differentiate them then afterwards from each other. And that's something bad and desirable. We don't want it to happen. So how can we solve this issue? Before I do the sampling process, I apply a filter that is going to get rid from all these noises or anything that's beyond my band of interest. We'll come back to this again and again. So, but this is the general, reason why do we need the anti-aliasing filter. Okay, so the anti-aliasing filter is again supposed to cut anything that's beyond my signal band. So it does not appear and come within my band of interest. Yes, Hamza.
Will this anti-aliasing filter, so it is somewhat working as a low pass filter, right?
Yes. Yes. If your signal is within, now we will see after a while that basically my original signal can be a band pass signal. It's not a base band signal. So in that case, you will need a different type of filter as anti-aliasing filter. Okay.
Yes, ma'am.
Yeah. So again, based on your question, if my basically original signal is a baseband signal, it's around bandwidth of it from 0, let's say, to FB here, or omega B, then I need an anti-aliasing filter that's a low pass filter to pass only the signal of interest. I don't need any of those extra copies before the sampling process, because all of them, they will, again, if I don't keep them, they will fold in on top of my original signal and cause that I will not be able to reconstruct it correctly. So this is what happens if I select my bandwidth. If I select my sampling frequency to be exactly double my bandwidth. So you can see that the copies, so this is my FS. So there will be a copy of the spectrum of the original signal around 0. There will be a same copy around FS, a same copy around 2FS. And again, in the negative frequency side as well, minus FS, minus 2FS. So you can see if you are sampling at exactly double the rate, double the bandwidth, they will be, how to say, they are adjacent, they are like kind of touching each other, but not interfering with each other, the two spectrums, the one after each other. Now, if you basically sample at a slow rate that is below your Nyquist rate, you can see now they will interfere with each other. So you will have a copy at 0, at FS, 2FS, but since your FS is less than double of the bandwidth, they will interfere with each other, and that's something bad. So it's not, that's why we have made the condition of double the bandwidth of your original signal. That's why that is the definition of the Nyquist rate. And this will also cause you a problem of aliasing. So again, remember that when you have an original spectrum, looks like this. Before the sampling, after the sampling, you will have a multiple copies of this at the baseband. It means at 0 Fs. At Fs, you will have a copy in the positive side and a copy on the negative side. I mean, so Fs of n plus n, Fs minus n, 2Fs plus n, 2Fs minus n, 3Fs plus n, 3Fs minus n, and so on and so forth. You will have also exactly the same on the negative side of the spectrum. So you will have exactly the same thing here. So now this is how it happened in the from a math perspective. Now we will start to little bit look into the circuit, what's happening from a circuit point of view. Okay, so the sampling, it's basically the process of discretization, means that I convert my signal from a continuous time domain into a discrete time domain. So the output of the sampling process is a discrete signal or a train of those discrete signal that they have different amplitudes. And again, we describe the sampling process by sampling frequency that have basically the distance between, or the time difference between two samples. Ts is equal 1 over Fs. Now, how can we perform the sampling in using a circuit? This is the simplest sampler. So you have a switch. The switch you can implement it using MOS transistors. And you have a capacitor that basically acts as a memory here or as a storage for the charge. So when the Vn is closed, means the Vn voltage, whatever voltage input I have here, it's being charged on this capacitor. And once this switch is going to open, now this capacitor is supposed to hold the value that was previously stored on Vn and move it to the output voltage here, V out. So that's how it happens. So once Vn is, the switch is closed, we are tracking the input voltage. Once it opens, we are supposed to hold this value until the next time the switch gets closed. So this circuit, either we call it a track and hold or sampled and hold circuit. We will describe them also, we'll come to the details of their implementation. Okay, so sampling basically again creates images of the signal, original signal in the frequency domain. So in the time domain, this is my original signal. After sampling, it becomes a certain pulses carrying a certain, with equal time difference between them. And basically, yeah, they have different amplitude here. Yeah, I have a question. So basically, where, I mean, how I'm going to control the sampling time here? Anybody?
And by the clock cycle, changing
Yeah.
the period of clock.
Yes, so where is the clock? The clock is basically controlling this switch. So when the clock is on, I can be closing this switch, and when the clock is off, then I open this switch. And that's why the clock frequency basically decides this Fs, the sampling frequency. So this is how they just want to make sure that you know how they are linked with each other. So now in the frequency domain, if this was the original bandwidth or the spectrum of my signal, this is how it will look like after. In sampling process, we will have again images or replicas from my spectrum of my original signal copied at the Fs, 2Fs, and every integer multiple of Fs. Again, remember that my Nyquist criteria is that I should have my sampling frequency at least 2 times of my bandwidth. So here, if my bandwidth is much less than fs means I'm doing a high sampling frequency. You can see now you have much empty bandwidth here, or a gap between your original bandwidth and your sampling frequency. If you are exactly sampling at the Nyquist rate, so here your fs is equal to 2w, so 2 of the bandwidth, and here you are exactly at the Nyquist rate. They are almost touching each other, and if you are sampling below your Nyquist rate, so they will basically mix with each other, and this causes that you are losing your information. So this is something undesirable you don't want to do. Now, there is basically something we call it subsampling. Something not too bad. I mean, we might be doing it intentionally. So this subsampling is that if you basically have your original signal is not, so just let's say that this is the first case when my original signal at FA is basically a baseband signal. So it's at low frequency in the first Nyquist zone, where it is basically less than half of Fs. So it's lying here. Now, once I will sample it, I will have a copies at all these red dashed lines. So that's and everything is fine here. I mean, there is no issue. Now, what if I have my original signal here at this FA here that is basically at far distance here with a B that is the same bandwidth that was here. Is this clear? So this is, I mean, the situation that I have here. So I have an original signal FA that is basically lying at a B distance from the sampling frequency Fs. And then I want to sample the signal with a sampling frequency that is Fs. So ideally, I mean, if I want to sample it normally, I would select a frequency that should be at least 2 times of this FA. But what if I sample it with a frequency that's just equal to Fs? Now this operation is basically, it's called undersampling. It's either harmonic, it has multiple names. And sometimes it has applications in the, for example, RF transceivers. So it's called direct IF to digital conversion, IF sampling, band pass sampling. So basically, once you will sample this FA, you will also have a copies of it at the same red dashed line here. So you will have a spectrum that is exactly equal to the spectrum that you were doing a good sampling for an original signal in part A that's shown here. So, I mean, we have spectrum after sampling process. In both cases, they are equal to each other. So that sometimes it has its own application, just we need to know it, that what is happening. And in this case, you can see it in the time domain, what is happening here. So if I have an original signal of 1 megahertz that was here, so this is, let's say, a 1 megahertz signal. Now I sample it with a frequency, sampling frequency of 20 megahertz. I'll be perfectly able to reconstruct the original signal. Now, what if I have a sampling frequency, a sampling signal, an original signal of 19 megahertz. So this is the 20, this moment. What if I had, so this is at, want to change the color. 19 megahertz. So it is just again 1 megahertz difference from the 20. This is the 20, the sampling. So in the time domain, what's happened? I won't be able to find out able to reconstruct the original signal of 19 megahertz. What I will find those sample points of that they replicate the 1 megahertz original signal. If I also do the same thing, if it was my original signal here was, so this is the 40 megahertz, 2 times 20, and this is one distance from it, so it's a 39 megahertz. They will again, after sampling, have exactly the same spectrum. So I will not be able to reconstruct the 39 megahertz, but I will find the 1 megahertz copy of it. Now this has sometimes application, intentionally they do this thing for its own application. Now just let's take this example. Okay. Now assume, yes.
The reason that we would not be able to get the 1 megahertz signal is that it will overlap or mixing of the data, right?
No, I'll be able to find, I'll think, I mean, let's call it, if you were not knowing in advance that you are doing sub-sampling process, your sampler will assume that your original signal is a 1 megahertz signal. So you need to know what you are doing, basically. That's, I mean, the moral of the story. Means you need to, and when you design your circuit, you need to know, are you doing subsampling or normal sampling?
So basically, in the previous slide, you shown that there is a scale of the first Nyquist, second Nyquist, third Nyquist, and so on.
Yes.
So it is our choice that what kind of in which region we have to sample our signal to get the to reconstruct the original signal without any kind of noise, right?
Yes, I mean, if you will only be able to, let's say, reconstruct the original signal only if it was lying within this half. In the first Nyquist, I'm pointing with my finger. If it is only lying within the first Nyquist zone, you cannot, if it was here and you are sampling with FS, if it was within this range or beyond, you will not be able to reconstruct the original signal. I mean, if it was in the second, third, or fourth, you will do a sub-sampling process for it, but you need to be aware that you are doing it and you are doing it for a certain purpose. Is that clear?
Actually, the problem is that I cannot get the practical image of this one. Means that how practically, if let's say I have a signal,
yes,
then using this scale, how practically I can sample this signal from using this thing that you are showing, like a subsampling or this thing.
Yeah, it has, as I told you, for example, in the RF transceivers, if you have a modulated signal that's at a certain carrier and you need to bring it to the baseband. Okay, so for example, you have a signal at 1 gigahertz, or let's say, sorry, your sampling frequency is 1 gigahertz, and you have a signal that is at 1.1 gigahertz. Okay, now when you subsample the signal at 1 gigahertz, you will return your signal, you will get a copy that's coming at 0.1 gigahertz, which is 100 megahertz. So this will be considered your baseband signal. Now, if you do a low pass filter here, you will recover this signal. So that's why it has a certain applications.
All right, I got it.
Is that making sense?
Yes, very much. Very much.
Yeah, thank you. Okay, so now just let's see this example. If I have an FM signal, I hope you remember what's FM signal, of 100 kilohertz at a band, basically. So this is bandwidth, the small, this thing is 100 kilohertz. This is a 0. And this signal is here, 10.7 megahertz. Okay. The signal is down converted. I mean, this signal is subsampled by how much sampling frequency? converted by how much megahertz? So what was the original sampling frequency? Is this question making any sense to you? So I had 100 kilohertz signal that I found it basically at 10.7 megahertz. That what exactly we were just saying. And you have so you have here certain so how can you return it back to the baseband here? Bring it here. What should you select your sampling frequency? And in this case, it's going to be sub-sampling. It's not a real sampling. And assume that you will have a copies of it here as well. So what does this mean if it's going to look like this? What should be your sampling clock?
I think it should be 700.
Yeah, just let's think about it loudly. Now, if we said that we will have, can I erase all these things? Why it's not erasing? I don't know what's not there. We will have a copies of the signal at FS, at 2FS, at 3FS, and at the baseband. So linking, you can see here, I have a 0 baseband. I have FS here, 2FS, 3FS, 4FS. So this is, assume this is 0, this is FS, this is 2FS, this is 3FS, and this is 4th FS. So what does this mean? How much your FS? Very simple math.
10.7 divided by 2, if you can see.
Yes, so it's a 5.35. So I mean, again, you will always remember that your spectrum will be replicated in the baseband at FS and all its integer multiples. So in the baseband here, the integer multiple is of a 0, so still valid. I mean, we are multiplying with all the integer multiples of FS, and at that each we are copying our spectrum of the original signal. So here our 2FS is basically 10.7. This is 2FS, then my FS is just 5.35. Now, again, we need an anti-aliasing filter that is supposed to cut everything outside my frequency band of interest. What do you expect this filter? I mean, an analog filter, you remember, we can have it either active filter using an op-amp based or a passive that just using a capacitor and resistor. So you expect this filter to be in working in continuous time or in discrete time, and why? Any idea? No idea. Okay, before
It should be working in the continuous time. Because,
yes.
After that, we have to then sample, and then we will have the quantization. So
exactly,
it should be for the CT.
Yes, exactly. Because when we are applying our anti-aliasing filter, we are applying it before we do the sampling. So at that time, still our original signal is in continuous time, and that's why my filter should be a continuous time filter. Okay, so before the sampling, before the sample and hold, this is my original signal in the peach color. Now, if I apply without anti-aliasing filter, so here there is no anti-aliasing filter, you can see that these noises here, spikes, which they are coming in the spectrum, they will fold back into my, so they will appear at the baseband, they will appear at FS, they will appear at 2FS, and so on and so forth. So they will now mix with my original signal, and that's something bad and desired. I don't want it. I cannot be able to get my original signal back. Now, if I apply this anti-aliasing filter, which you can see here, it's a low pass filter in the continuous time, I am going to get rid from those pulses, noises. I will reject them out, and I will have a clean copies of my original signal at the 0FS, FS, 2FS, and so on and so forth. Is everyone clear about the need for anti-aliasing filter? Any question about it? Okay, I hope everything is clear. Yeah.
You just said we apply anti-aliasing filter after before sampling.
Yes.
Aren't we applying this after sampling? I'm a bit confused about it.
Sorry. Yeah, we are applying it before sampling.
So I think I'm confused, but we should apply it after sampling.
Why you should apply it after sampling?
To get a single alias of the whole signal of.
Yeah, because now when you will basically
we get different alias of single signal, sampled signal. So we want to get a single alias from all of that.
No, I mean, because the problem comes when you will do the sampling, that basically anything that's outside of your band of interest, they will fold back and come in your, on top of your original signal. So now you have two signals on top of each other. I mean, mixing with each other. How you will differentiate between them? That's the problem. Okay, now you're confused is here basically when you will get the signal, it has a multiple replicas of your original signal. Now in the digital domain, you will basically work in the digital, so that's a different thing. You will be understanding, I mean, it takes care of this. Now when we will reconstruct this signal to an back to analog, we will need to get rid from those in order to just get this original signal. And that's why we need a reconstruction filter. So we are coming back to that. We are going there. Okay. So if just to emphasize on this, if I want to sample normal sampling of my baseband signal, my anti-aliasing filter, what is my choice? Low pass, band pass, or high pass filter? I'm going to select a low pass filter. Now, if I am doing a subsampling of an RF pass band signal, my anti-aliasing filter is going to be a band pass filter. Sorry, and that's basically coming back to the point here. If this was my original signal, and before I want to subsample it, if there was anything that was here in the baseband, for me, it's just considered as a noise at this moment. So before I want to subsample, I will take a band pass filter here to just take this original signal and then subsample it. So when I will go to the, it will come in the baseband, it will be clean, it will not mix with anybody else. Okay, so this was we just said. Now let's see this example. If I have a signal that has the band from 33 megahertz, so this is 33, until 39 megahertz. Okay, so this point is 39, this point is 33. So it has a total bandwidth of 12 megahertz. Sorry, 6 megahertz. And we can see that it's a not a baseband signal, it's a passband signal. So what sampling rate would I choose to bring the signal to the baseband here? From 0 to 6 megahertz. Which one of those will I select? Obviously, it's going to be
19.5.
sorry?
Could be 19.5.
Let's think about it. Again, remember that whenever I am going to multiply it, whenever I'm going to do the subsampling here, so this is subsampling, I will get a copies at the baseband, I mean, at 0 of fs, at multiples of fs. So if I apply the 78 mega sample per second, will it goes to the baseband? No. Why? It will appear basically at k fs minus or plus minus, I think it was of this bandwidth of it. I hope I am doing correct. Was it correct? I think so. Okay, so now if I apply 39 megahertz, it will come to the baseband. If I apply also 19.5 megahertz, sorry, mega sample per second, it will also come. And if I apply 13, it will also, you will get a copy in the baseband. This one will not come to the base band because of it. Just let's remember the math. So these where the images, they will come. So they will come at K, Fs plus minus Fa. Fa is our bandwidth. Okay. Okay, now what is the case for those? I mean, what is the advantage or disadvantage? So here, if I'm doing at 39, at 19.5, and at 13 megahertz, what is the advantage and disadvantage of each one of this? Why will I select the 39 or I will select 13 or 19.5? I mean, if I'm asked you from perspective that we have advanced digital circuit, I mean, I'm working at low nodes and I can gain from the digital circuits. Which one you would select? Any idea? Okay, let me make it, give you a hint. Now, if I'm going to do before the sampling, the anti-aliasing filter, okay? So I can have a filter that looks like this, or I must have a filter that is basically like this, or have a filter like this. And these filters, we said it will be in the continuous time, and they are analog filters. So which one you would select? Which option?
39 would be.
Yeah,
39.
39. Why? Yes, the answer is correct, but why?
As
फिर
another
39 इसलिए सेलेक्ट करेंगे क्योंकि जो एनालॉग फिल्टर बनाएंगे
Can you
वो
speak in
हम कम
English?
ऑर्डर करके बना यस
Yes.
फॉर एनालॉग फिल्टर
Yes.
if we select 39 sampling frequency we can select analog filter of lower order. If we
Exactly.
select
Yes.
13 mega sample so we need to select analog filter of higher orders.
Yes, exactly. The reason is correct. And the answer is also correct. So basically, if you need to select the 13 megahertz, you will have a lower clock frequency. You may save in your power consumption, but the issue is that you need a sharper filter, a sharper cutoff filter, and this means that you will need a higher order filter in the analog domain, and this will make the complexity more. Now, we said we have advantages in the digital circuits. So if I make my life easier by choosing a low order filter in the analog domain, and in the digital filter, so in the digital domain, I can do either subsampling. We will talk about it again, the subsampling process, or sorry, not subsampling, we call it a decimation process. We will describe it now. Then I can basically gain the advantage from the analog, from the digital circuits, and reduce the complexity in the analog domain. Okay. So now if I, again, related to this point, if I basically work at the limit of Nyquist criteria, I will need an ideal filter, which is difficult to design or even does not exist. So signals in the alias band, which is the alias band is basically here, and then let's call it from the bandwidth of my signal until the FS, those any noises that comes here, they will basically alias back. They will come into my desired band of interest after aliasing. So I want a filter, anti-aliasing filter that rejects these noises here. Okay, so now if we look at this plot here, that's showing me the suppression in dB, how much I will cut or suppress my those unwanted signals, and with respect to the sampling frequency divided by the bandwidth of your signal. You can see that this Fs divided by bandwidth is minimum equal to 2. Why? Because this is the Nyquist limit, I mean, Nyquist rate. So this is the minimum that I can select, that Fs is basically double of the bandwidth. So Fs over double bandwidth is equal to 2. In this case, whether you compare the first order, second order, third or fourth filter, all of them, they are giving me low suppression. But if you basically take just an example of a fourth order filter, how much suppression will it give us for a filter? For sorry, the noises, a fourth order filter. How much do you expect it gives us suppression? Any idea? Now, fourth order filter means that it has how many poles in its transfer function?
4 poles.
Yes, it has 4 poles, and we know that each pole is basically gives you a slope of minus 20 dB per decade or 6 dB per octave. Octave means you double it, your frequency. So now this is the ideal. Just I want a different color. This one. Okay, so if I, in the ideal that it comes here and at the cutoff frequency starting from the pole frequency or FC, the cutoff frequency of the filter, you will have this minus 20 dB per decade slope. Now, if they were more, you will have 2 poles, you will have minus 40 dB. If it is a 3 poles, you will have minus 60 dB per decade. Fourth, you will have minus 80 dB per decade. But in reality, it does not just start at this particular point and start decreasing. This is basically a simplified model. In reality, at this FC, we have an amplitude that is minus 3 dB from this maximum value. If I have, let's say here, 0 dB, this point at the FC, it will have, each pole will cause it to be minus 3 dB from that original value. And that we discussed in the microelectronic design, as far as I remember. So 4 poles means that you will have, each one will contribute minus 3. So minus 3 times 4, you will have minus 12 dB. So here I have at the 4 pole, it will be 12 dB suppression. Any question? No question on this? Okay, is there any maximum limit on the sampling frequency you can use? Yes, in a sense that you need to be careful. You don't go too much, increase your sampling frequency, because your power consumption will also rise accordingly. It will increase by increasing sampling frequency, and you need to be careful when you design that much high frequencies. You will run into other issues. Now, if we take any, yes?
What this minus 12 dB actually represents here, actually, what this says?
It
This
says
minus
that,
12 dB.
yeah, it says if you were basically having any signal that is, let's say, in this band, or it will have that these noises, if it has a magnitude, let's say, of originally 50 dB, 12 dB suppression means that your amplitude will be decreased by 12 dB. Of that, from 50, it will become 50 minus 12, so 38 dB. Which is still, I mean, 38 dB is large. But if you go for a 60 dB, then it will become minus 10 dB from its original value. And that means that you have shrinked it significantly. Okay.
So which one we will select from the order? Should we select the first order, the second order, or the third order according to that?
That depends on the ratio that you have here, your FS over your bandwidth. And that's what we were talking here. If you were having a large FS over bandwidth ratio, then you can select a low order. If they were medium, then you need maybe a second order. Here you need a very large order, and that's what we are seeing in this figure here, the same information. So your FS over your bandwidth will tells you which one you should, I mean, if I have FS over bandwidth of a 10 ratio, you can see in this dotted line, I will get a 20 dB suppression if I use a first order. If I use a second order, I will get around 40, around 60 by third order. So every order gives me 20. So it depends on your application, how much you selective your FS over bandwidth, and how much you expect that you have interference around, or those noise that you want to get rid from them. If you think that there might be a strong interference, then you should go for a higher order, or you should increase this ratio more. You go for more oversampling ratio. Okay.
Got it.
Yeah, so the oversampling means that you increase your sampling rate or increase FS to be FS much larger than your bandwidth of your signal. It basically relaxes the requirement of the baseband anti-aliasing filter. So you can see here you need a sharper filter in order to get rid from those noises. While here with the frequency, sampling frequency is higher, you have a lower slope filter, which makes it easier to design in the analog domain. Now we have another thing that we call is basically opposite of increasing the sampling frequency is to do decimation, which is basically after, for example, you did high sampling frequency in the analog domain, you did a high sampling frequency, but you don't need all of those samples. You can do a process to get rid from those samples, and it's called, this process is decimation. So if we look at it in the time domain perspective, if this is my original signal before the sampling, and after sampling with the high frequencies, you will have a lot of samples. Decimation means that you discard some of those samples. So after, let's say, every one sample, you discard one. So I get rid from this, I get rid from this, I get rid from this one, and from this one, and so on and so forth. So it means that I am basically, if you look at it now from frequency domain perspective, it means that I am sampling now by a lower rate than my original sampling frequency. So if here was this, you can see my TS here and my new TS, it's double of it. So this means my sampling frequency is half. This FSD is half of the original FS. So now we will have the copies of the original signal spectrum will appear at lower frequencies, at the copies of FSD and not the two FSD. So this is the definition of the decimation. Now, why somebody would need this decimation? Why didn't I then from the beginning sample with this desired sampling frequency that I need? The process is, the reason for that is that why I did oversampling in the beginning so that I can relax my anti-aliasing filter and have then at more distant, you can see now my anti-aliasing filter can be very relaxed in terms of design. Now, once I went to the digital domain, I have more flexibility. I can design higher order filters that they are basically much easier in the digital domain and cut all those undesired replicas of my original signal. So that's why to gain from the advantages in the digital, I can do first oversampling in the digital initially, and then decimate my signal to get rid from those some of the original samples to get a lower sampling rate that I, in the first place, wanted it, but didn't use it just because I will have requirement of a higher order filter, anti-aliasing filter. Yes, Roshan, you were raising your hand.
Ma'am, can you please repeat this?
Okay.
Why do we do this?
Yes. your target initially is to use an FSD, this low sampling frequency. Okay, that was your original target for your application, okay? Now, if you were to use this one, you would need to have a sharper filter as an anti-aliasing filter in the analog domain, and that will make your design more complex. So what you are going to do, you are going to sample at a higher frequency, but you don't need it. You just sample at a higher frequency to make your design of anti-aliasing filter more easy. So you make your life easier. Just take a second, maybe order filter, and that will solve your problem. Now you went to the digital domain. You are more relaxed in doing what you want there. You can design any order filter you want and have very sharper filter. So now you can go back to your desired sampling frequency by doing this decimation process, and you have the choice to do anti-aliasing filter of very sharp response, but this has to be a digital filter, and therefore you can basically select whatever order that you want, so that will be easier for you. Is that making sense to you?
So actually means that what we are doing is reducing the cost as well as the power from sampling and the use of the filter, right?
Yeah, so basically we made our life easy, but I don't want to continue in all the digital parts with this very high frequency. I don't need that much high frequency for my application. I can reduce it before I do all the other processing, and that's why it's a sub-sampling process. Sorry, a decimation process is again like a sampling at a lower frequency than what we originally have. Okay. Any question on this?
Ma'am, what I don't understand is that हम जो हैं हम anti-aliasing filter we do it before sampling. So how does it affect के हमारे anti-aliasing filter का मतलब in the frequency domain उसकी bandwidth तो वही रह रही है. So how does it affect के
Roshan, remember to speak in English.
yes sorry in the frequency domain the
Yes.
bandwidth is the same. So how does it affect the anti-aliasing filter? Because we use it before sampling. So that keeps confusing me. Okay, why are we using?
This one here, you mean it's basically you want to get rid anything that is, let me go back, in this band from fs minus bandwidth until fs. We
Yes.
want to get rid from anything here.
Yes.
Okay, so anything in
Yes.
this area we want. So now if fs is small, you are more near to your original signal. Yes.
Yes.
This means you need a sharper filter to cut this smaller area. While if you're fs way far there in the frequency, then you have a more time, or you can have a lower slope to cut that band from fs minus w until fs.
Oh, okay.
You got it? So again, this line is important for you. We signals in this band fs minus w minus bandwidth to fs, those anything that's here, they will alias back into our original signal, and therefore we want our anti-aliasing filter to suppress them. Therefore, if this, again, this is bandwidth, this is fs, and this is fs minus bandwidth. Now, if this point is very far from this point, then you can have a more relaxed filter. If they are near to each other, then you need a very sharp filter to cut this region. Okay?
Yes, I get it.
Okay, so now just because here it is in the digital domain, the decimation, you will also need to apply this digital filter to have the subsampling process. Okay, otherwise those copies which they were here, they will also come fold back. So we will know, I mean, before the decimation, we will need this anti-aliasing filter. Okay, so now we have on the opposite side, you remember in the beginning, we talked about the entire chain of the mixed signal system. So now we done the processing. We have our original signal that looks like this. I mean, it's a copy of it at 0 to fs, at fs, 2fs, 3fs, and so on and so forth. So now, what's the DAC, digital to analog converter, supposed to have? So in the time domain, I mean, my signal looks like this with the digital codes that they were here. But now, I mean, that is in the ideal case. I mean, I don't have in the analog those impulses. They will have a certain width. So they will basically not, that's not not a realistic signal to have impulse in the physical, there is no physical meaning for that. So basically, what is the DAC supposed to do? If those, just from an easy point of view, describing that, if those are my impulses and my DAC comes and connect those points with each other to have a back and a voltage signal, a continuous signal. Now this line here connecting between them is basically a first order function, yes? First order interpolation, yes? And the first order have the equation y equal m times x plus c. Now, is the first order interpolation is a good thing or bad? Means, let me rephrase my question. If you have two impulses here, and you want to make the function continuous by connecting them with each other. I mean, if you connect them with a straight line, so you are anticipating or you are interpolating that all the points between those 2 points, they are basically following a straight line. My question, if you have taken a numerical methods, I don't know.
Yes, ma'am, this is y is equals to mx plus c is a straight line equation, and I think it would do work. Otherwise, there's an equation like y2 minus y1 upon x2 minus x1.
Yeah, so basically we try to find, I mean, we need to make a choice of what are those values that between those 2 points, because again, they were discrete in the digital. We want to make them continuous in time. So we need to make something between those 2 points. Again, because in the digital, we said we don't have infinite number of values. We have taken those values with after every TS time. So what is in the middle, we need to make a choice for it. So one way is that you can assume that it's a straight line between it. I mean, this is not only, let's say, the only option that we have. You can go with the higher order functions here, second order, third order, or what some others, but obviously you will go with a higher complexity if you make those choices. What about, is there anything simpler than a first order? What do you say?
We can just hold the first,
Yes.
like in the
Yes, you can hold the value. Keep the, let me not show in another color. So you can hold the value here. And now this time here, until if this was the case, you will go, this is the third sample. And so this is called a zero order hold. I mean, it's bad than a first order, but it's a simpler in implementation. So this is called a zero order hold. So what is the DAC in reality doing? It's going to give you the value and hold it until the next clock cycle, and then it will change the value and keep it constant for that entire cycle. Okay, so this is basically, so the DAC is basically needs to reconstruct the original signal. In the time domain, the reconstruction filter is basically interpolate, restores, or reconstruct the signal. And the reconstruction filter will suppress those images. Now we will discuss this basically in detail. So now in order to going from this, the impulses into those pulses in terms of math, what's happening? Do you know? It's like I am what? Multiplying my or convoluting my original signal with a train of pulses here, not impulses. We are convoluting our signal with the train of pulses. So what is, this is the train of pulses, and what is the frequency domain representation of the train of pulses? Anybody remember?
The sync function.
Yes, it's a sync function. And this sync function basically will have nulls at those where 1 over TH. So the null at any frequencies that basically 1 over TH. So if this here TH is half of TS, this means I will have where my nulls at 2 of my sampling frequencies. The nulls, they will come almost, I mean, this figure is not drawn good. Now, if it was at basically here, your TH is 1/4 of your TS. So the nulls, they will come where? At 4 times of our FS. And if TH is equal to TS, then you will have at those multiples. At FS, 2FS, 3FS. So he will have a 2FS, 4FS, 4FS, and then 8FS. Okay. So this is basically the sync function. Now, if you look, if it has to happen a convolution in time domain with those pulses, what's going to happen in the frequency domain? What will happen to our original signal? How the spectrum after the DAC will look like means what? This is my question. Again, DAC will cause my original sampled signal to convolve with train of pulses in, sorry for my writing, in time domain. What is going to happen in this frequency domain? So easy. If it is convolution in time domain, what is it in frequency domain?
Multiplication with the same function.
It will be multiplication. And we will come back to it. I think I already crossed my time. So remember that just revise this part for next time, how convolution is related to the, we're almost done here already, that convolution in time domain is just multiplication in the frequency domain. So I'll multiply this spectrum of the sync function with my original singular. And you can see that it's already almost looking like a low pass filter. So that's why I will get rid from those images of my signal, but I will not get rid from them very goodly because of those lobes here. Therefore, we will still need a reconstruction filter, which is also a low pass filter, to get rid from them completely. Any question?